Hello everyone. I hope you all are good. The topic that we are going to discuss today is current electricity, NCRT section 3.1 to 3.3. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. So this is the index of the topics that we are going to discuss today. First one is NCRT section 3.1 introduction, then NCRT section 3.2 electric current, and then NCRT section 3.3 electric currents in conductors. Okay, the first one is introduction. All charges, whether free or bound, we consider to be at rest in chapter 1. Okay, so in this chapter we are dealing with moving charges. Okay, current. What is current? Due to moving charges. Okay, in last chapter, chapter 1, what we have discussed, stationary charges. Okay, the charges that are on the surface or in the bulk in the form of any distribution but stationary, whether they are free or bound. Okay, in the case of conductors we took free charges, and in the case of dielectric we chose bound charges. Okay, in dielectrics there were bound charges, in conductors there were free charges. Okay, so all the charges, free or bound, okay, we considered to be at rest in chapter 1. Okay, in conductor charges accumulate on the surface. Okay, we only dealt with stationary condition, static condition. Okay, when we start any question, we start with in steady equation. We started with in static condition. Also in capacitor, we started as in static condition. Okay, when charges are stationary and distribution of charges completed. Okay, so charges redistribute themselves and become stationary. We didn't deal with flow of charges, movement of charges in the chapter 1. Now in chapter 2, what we are going to do, we are going to deal with moving charges. Okay, charges in motion. So moving charges create electric currents which occur naturally in various situations. Okay, moving charges produce electric currents, and in nature, okay, in our households, everything, almost every electric device, every electronic device, okay, around us is working with the help of electric current. Even the things that are working with the help of batteries or cells, like our clock, okay, wristwatch, torch, or anything else that is working on some toys that are working on batteries or cells, okay, they are also working on electric currents, but the amount of electric current is small in this case. Okay, so this small amount of current is sufficient for that torches, or like in torches there are LED bulbs, they only consume very less electricity, so small amount of current is sufficient for them, so they are operating on battery. Also clocks, they are operating on battery. Okay, other appliances that need more current, okay, so they are working on direct supply of that we use in our household, okay, from electricity department. Okay, or what amount of current is in the household normally. So jo normal appliances, electric appliances that are working on 5 ampere current, okay, except some other appliances like air conditioner or geyser, heater, etc., they are working on high current, more than 5 ampere. Okay, normal appliances work on 5 ampere. Lightning is a phenomenon where charges flow from clouds to earth through the atmosphere. Okay, so lightning is very common phenomenon that is due to the charge flow from clouds to earth through the atmosphere, sometimes causing destruction. Okay, so when there is a charge flow, a large amount of charge flow from one material to another, there is a discharge, large amount of charge discharge, charge leakage. Okay, due to which a spark, a discharge is produced. Okay, in the lightning, large amount of charges flow from clouds to the earth. Okay, or from one cloud to another cloud. Okay, so this is a lightning phenomenon. When these charges flow from clouds to earth, then it will cause destruction. When they flow from cloud to cloud, then there will be no destruction because they are flowing from cloud to cloud. They are not striking the ground. Okay, when they strike the ground, there will be destruction. Okay, so what is the mechanism of the lightning? How charges flow from clouds to earth? Okay, so let's suppose there is a cloud on the above and it is charged. Why it is charged? Due to the collisions of clouds with each other, or in between there is a water droplets. Okay, and also water is condensed, ice may be present, ice crystals may be present, due to which friction or colliding with each other, charges are produced on the clouds. Okay, so these charges on the clouds, when clouds pass over the ground, they induce the charges in the ground also of opposite polarity. Okay, so therefore a potential difference is created between these charges, between clouds and earth, ground. Okay, so due to this potential difference, then between clouds and earth there is air. Okay, so when this potential difference is increased and becomes more than the breakdown limit of the air. Okay, we discussed in the capacitor. What is the breakdown limit of the capacitor? Is of the order of 10 raised to power 6 volt per meter. This amount, this order of electric field is required. Okay, so potential difference is increased and electric field between these clouds and earth, ground, is above the, or is of the order of 10 raised to power 6 volt per meter, then electric discharge happen. Okay, so large amount of charges flow from clouds to ground, due to which lightning phenomenon happens. Okay, so also you may have seen that trees burned due to the lightning strike. Okay, so this is due to this phenomenon. Now this is the diagram. Okay, so these are the clouds. So and the lightning or thunder is striking the ground like this. Okay, lightning. While lightning involves unsteady charge flow, many everyday devices demonstrate steady current flow similar to water flows smoothly in a river. Okay, in a lightning, what happens? Initially no charge is flowing because breakdown limit is not reached. When breakdown limit is being reached, then large amount of charges at once flow from clouds to the ground. Okay, so this is unsteady flow. This is not steady. Initially no charges are flowing, then at a sudden large amount of charges begins to flow. Okay, but these are unsteady. But in everyday devices that we are using in our houses, like fan, okay, lights, tube light, or any other appliances, so they use steady current. Okay, so normal devices use 5 ampere steady current. Okay, there may be range, some small or some small variations from this 5, but this is steady amount, 5 ampere current. Okay, normally, so they use this steady amount of current. Okay, so beside this unsteady charge flow, many everyday devices demonstrate steady flow similar to water flowing. You can draw an analogy that water flowing smoothly in a river. Okay, like this we can say a steady flow, a smooth flow of current. Okay, so you can make analogous with the flowing river. So common examples include torches and cell driven clocks. Okay, so what is, we know that torches and cell driven clocks, they both work on batteries or cells. Okay, so we can say that current is only in the household So can we say that only household appliances use electric currents? No. These torches and these cell-driven clocks also work on electric currents, but that electric current is very small as compared to the electric current that our normal household appliances, electric appliances, that fans or tube lights are using. Okay, so in torches there is LED bulbs. Okay, so these LED bulbs require very small current or very small potential difference across them. Okay, so which cell or battery can fulfill. Okay, a normal cell, small cell, is having 1.6 volt or 1.5 volt. Okay, so these LED bulbs work on this small potential difference also, but in our normal household appliances they work on 220 voltage. Okay, so they work on 220 voltage, but these torches or these clocks can work on 1.5 volt. Okay, some clocks may require two cells, so because they can work on only a potential difference of 3 volts. So 1.5 1.5, two cells of 1.5 volt can be used. Okay, so this is a example. So this is the diagrammatic representation. So this is a cell. Okay, and this is positive terminal, this is negative terminal. Okay, you may have studied in chemistry electrochemical and electrolytic cells. Okay, so what is electrochemical cell? Electrochemical cell, there it converts chemical energy to electrical energy. How? There is some reaction going on in between the cell. Okay, so due to which positive charges accumulate on this positive terminal and negative charges accumulate on this negative terminal of the cell. Okay, due to which a constant potential difference is maintained till reaction is going on. Okay, so this is spontaneous reaction. It is going by itself and for a long time. You may have seen that for a cell, when we put it in clock, it worked for 2-3 months. Okay, it means the reaction in between the cell is going on for 2-3 months. After that, that reaction stop, and that potential difference that is maintaining due to this chemical reaction also vanishes. Okay, due to which cell stops working. So due to this chemical energy, due to these chemical reactions, there is positive potential maintained and there is negative potential maintained. So potential difference is maintained, due to which when we connect a bulb with this cell, okay, so this wire is conductor, so it will have free electrons. Okay, so this is positive terminal, so electron will attract towards this positive terminal and repelled by this negative terminal. So flow of electrons will be from negative terminal to positive terminal, like this. Okay, but direction of current is from positive terminal to negative terminal. Why? Because initially when it is not known that electric current is due to the flow of electrons. Okay, so the scientists assumed that, and other people assumed that direction of current is due to positive charges. Okay, so they assumed that direction of current is from positive terminal to negative terminal. Okay, but afterwards when it is discovered that flow of current is due to flow of electrons, then but direction of current is also was not changed even. Why? Because they have many things or derivations or concepts driven at the time when it was known. Okay, when it was when they came to know that the electric current is due to flow of electrons, then at the time many things have been derived using the traditional direction of current, which is from positive to negative terminal. Okay, so they didn't change the direction of current, they only said that direction of current is in opposite direction of flow of currents, electrons. Okay, they didn't change the direction of current. They only said that flow direction of current is in the direction of opposite to the flow of electrons. But we know that current is due to flow of electrons only. Okay. So this figure is showing direction of current is opposite to the direction of flow of electrons. In this chapter, we will study the fundamental laws governing steady electric currents. Okay, so in this chapter, we will study some fundamental laws that govern the steady electric currents. Steady means smooth flow of current, not variation, not unsteady charge flow. Okay. So objective 3.2 electric current. Objective is to understand the electric current definition, measurement and units. Okay. So this is the again diagrammatic representation. So here is a copper strip. So since it is conductor, much amount of free electrons are present in this. Okay, when we connect this copper strip with the battery, external source. Okay, so this is the positive terminal of battery, this is the negative terminal of battery. So due to this positive terminal, electrons in this copper strip feel attraction towards it, and due to this negative terminal, electrons in this section feels repulsion from that side. So electron will start flowing from this side to this side. Okay, from negative terminal to positive terminal. Okay, so this is the direction of flow of currents, flow of electrons that is being shown from negative terminal to positive terminal. But conventional direction of current is taken as opposite to the flow of electrons, which is in the opposite direction of flow of electrons. Got it? Direction of flow of positive charges is opposite to the direction of flow of negative charges. So it is assumed earlier that current is due to the flow of positive charge. So we can say that direction of flow of positive charge is opposite to the direction of flow of negative charge. Okay. Imagine a small area held normal to the direction of the flow of charges, allows both positive and negative charges to flow forward and backward across it. Okay, we can assume a cross-sectional area in between like this, which is held perpendicular, means it is perpendicular to the flow of electrons. It is perpendicular, it is cross-sectional area. Okay, so it is perpendicular to the length of this copper strip. So imagine a small area held normal to the direction of flow of charges, allows both positive and negative charges. Okay, we are considering both positive and negative charges. In case of conductors or metals, free charges are electrons. But in case of, if there is electrolytic solution, then there will be positive and negative ions both, due to which current conducts. Okay, due to which current flows. So we can imagine a small area held normal to the direction of flow of charges, allow both positive and negative charges to flow forward and backward across it. Okay, so we are considering one area which will allow both positive and negative charges to flow across it, in the forward direction also, in the backward direction also. During the time interval t, okay, during any time interval t, Q positive represents the net amount of positive charge flowing forward. Okay, so what is Q positive here? Net amount of positive charges flowing forward. Okay, what is net amount? Suppose I can say amount of 5 positive charge is moving forward direction. Okay, 5 positive charges are moving in positive direction and 2 positive charges are moving in backward direction. Okay, so what is the net amount of positive charges flowing forward? 5 minus 2. Okay, the charges that are moving in forward direction minus the charges that are moving in negative direction. So this is the net amount of positive charges flowing forward. Okay, while Q negative represents the net amount of negative charge flowing forward. Okay, so what is Q negative again? Net amount means forward negative charges minus the negative charges that are moving backward. That is net amount of negative charges that are flowing forward. Okay, if 5 negative charges are flowing forward and 2 negative charges are flowing backwards, then net amount of negative charges flowing forward is 5 minus 2, 3. Got it? So net charge flowing across the area in the forward direction is Q equal to Q plus minus Q negative. Okay, so this is the net charge flowing across the area. Okay, net charge means positive as well as negative. So what is net charge flowing across the area in the forward direction is given by Q positive minus Q negative. Okay, by this expression. For steady current, this is proportional to T, and the current across the area in the forward direction is defined as. Okay, for steady current, we can say this Q is proportional to T. Okay, the amount of charge flowing in the forward direction is proportional to T, means it will depends on time. Okay, if time interval is large, the amount of flow of charge that is flowing in the forward direction will be more. If time interval is small, this flow of charge will be less. So it will be proportional to time interval T. And current across the area in the forward direction is defined as, so how we will define the current across that area? So it is given as I equal to Q by T. Okay, the amount of charges in a given interval. So amount of charges that are flowing through any cross-section area in a given time interval is known as current. Okay, or we can say amount of current, amount of charges per unit time is equal to current. Okay, so how many charges, how much amount of charges is flowing through that cross-section area that is held perpendicular to the flow of charges in a unit time is known as current. So this is 3.1 equation. When the resulting value is negative, it indicates current flowing in the backward direction. This thing, Q equal to Q positive minus Q negative. If the resulting value is negative, this Q, net Q is negative, then it means current flowing in the backward direction. Okay, so why it will be negative? If electrons are moving in forward direction, okay, in the case of conductor, you can take, in case of conductor, this Q positive is 0. Charges due to positive, current due to positive charges is 0, because in conductors there is no positive charges, only electrons, free electrons. Okay, so they are moving in the forward direction. Okay, so Q negative, this Q negative will be positive term, because Q negative is the net amount of charges, negative charges that are flowing in the forward direction. So electrons are moving in all the electrons are moving in forward direction. So Q negative will be, amount of this Q negative will be positive. Okay, so minus of this positive value will be negative. So this net Q will be negative. So if the resulting value is negative, it means the current flowing in the backward direction. If the electrons are moving in forward direction, then the current is in backward direction. It is representing that thing. Okay, since currents are not always steady, a more general definition is needed. Okay, so we are assuming that current is steady. If current is not steady, okay, if it is unsteady, it is changing with time. Okay, now it is 2 ampere, after some time it will be 5 ampere, after some time it will be 8 ampere. Okay, so it is not steady, it is changing with time or any other quantity. Okay, since currents are not always steady, a more general definition is needed. What is more general definition? Is for instantaneous current. Means we want to find a current at some instant, at this time, not in an interval. Okay, not in an interval, on a specific time, at an instant. That is instantaneous current. So what will be the expression? So consider, since consider delta Q as the net charge flowing across a conductor's cross section during time interval delta t between t and t delta t. Okay, so assume that delta Q is the net charge flowing across a conductor, okay, cross section during the time interval delta t, that is between time t and t plus delta t. Okay, there is some time t and there is some time t plus delta t between these time intervals, between these times. So t plus delta t minus this t, this is the time interval delta t. Okay, a time interval within which we want to find the current. Okay, current at time t. Now this is delta t, this is full interval. Okay, if this current charge is steady, flow of charge is steady, that is, if we assume that 2 coulomb charge is passing at a steady rate, so in a time interval we will find the current that is steady. But if flow of charges is varying, at some time it is 2 coulomb per second, at some time it is 4 coulomb per second, so the variation of the flow of charge will result in non-steady current, okay, unsteady current. So current at time, we want to find the instantaneous current at some point of time. So across the conductor cross section is defined as, so current at a time across the conductor cross section is defined as IT, which is the current at a time. So limit delta t tends to 0, delta Q upon delta t. So this is what, this is the charge flowing across the conductor upon the time interval. Okay, this is current. If the current is steady, this formula is valid. But if current is not steady, this formula is not valid. We have to put the limit. What is this limit? This is delta t tends to 0, means if this time interval is nearly equal to 0, but not 0, nearly equal to 0, it means we can say tends to 0. It is tending to 0. Okay, it means we are reducing this time interval to a point of time at an instant. Okay, so we are suppressing, we are reducing this time interval to a point, an instant. Okay, so this is the limit. So we are finding this I, current at time t, which is we can find after putting limit delta t tends to 0. Okay, SI unit of current is amperes. Okay, you may also have studied in class 10th that SI unit of current is ampere. Okay, 1 ampere is equal to 1 coulomb per 1 second. Current is equal to Q by T. So SI unit of charge is coulomb and SI unit of time is second. So SI unit of current is 1 ampere. It is also fundamental unit. Okay, one out of 7 fundamental units, which is ampere. Okay, 1 ampere equal to 1 coulomb per second. Domestic appliances typically operate at currents of order 1 ampere. Okay, so domestic appliances typically operate at order of 1 ampere. Means 1 ampere means we define the order like this. If we can say 10 raised per 8, we mean that the current is if value of current is this, suppose any value 3 into 10 raised per 8, we can say current is the order of 10 raised per 8. Okay, we will see this order, that how much power is 10 is raised to what power. So we can say this is current is order of 10 raised per 8. Okay, so now it is written that domestic appliances typically operate at current of 1 ampere, which means 10 raised per 0. 1 ampere order. Okay, so we know that current for domestic appliances, normal domestic appliances, current is 5 ampere. Okay, so there may be very small variation, but it is 5 ampere. Okay, so it is of order of 5 into 10 raised per 0 ampere, means 1, which means order of 1 ampere. It is of order of 1 ampere. So domestic appliances generally operate at current of order of 1 ampere. Okay. And average lightning, we have discussed about lightning. So average lightning carries currents of the order of tens of thousands of amperes. Okay. So average lightning carries current of 10,000 ampere, means 10,000 means 10 into 1000 means 10 raised power 3, which is 10 raised power 4, that order of current. Okay, it may be 2 into 10 raised power 4, it may be 3 into 10 raised power 4. We are not concerned with that. We are concerned with order. So it is of order of tens of thousands of amperes. Okay, and average lightning carries that amount of current, a large amount of current. And at the other extreme, currents in our nerves are in microamperes. Okay, there is also small amount of current flowing in our body due to flow of charged ions like sodium ions, okay, that are flowing in our bloodstream. Okay, due to this flow of charged ions, there is small amount of current which is of the order of microamperes, 10 raised power minus 6 ampere, that is flowing in our nerves, that is undetectable normally. Okay. So now we have came to 3.3 section of NCERT, electric currents in conductors. Okay, so this is the conductor, cylindrical conductor having two dielectric discs on its end. So this disc is charged with positive charge, this disc is charged with negative charge. Okay, so what is this figure showing? Charges plus Q and minus Q put at the ends of a metallic cylinder. The electrons will drift because of electric field created to neutralize these charges. Okay, so these two ends are charged, and this is charged with plus Q charge, this is charged with minus Q charge. Okay, then electric field will set up from positive charges to negative charge like this. Okay, and electron will feel the force in the direction of opposite to the electric field. So electrons will start moving in this direction, in the opposite direction of electric field. Okay, so now these electrons will combine with these positive charges and neutralize them. Also, due to movement of electron in this direction, in this section there is positive charge, there is accumulation of positive charge, so it will neutralize this negative charge. These positive charge will neutralize this negative charge. Okay, so both these positive and negative charges will be neutralized by the movement of electrons. Then if these charges are neutralized, then electric field vanishes, potential difference vanishes, and due to which current will stop flowing. Current will start flowing initially due to the potential difference created, due to the electric field created. Electrons start moving and current will start flowing. After electron neutralize this positive charge and positive charges neutralize these negative charges, then electric field vanishes, due to which movement of electrons also stopped, due to which current will stop after a while, unless the charges plus Q and minus Q are continuously replenished. So plus Q and minus Q are continuously replenished, continuously finishing because of this movement of electrons, and till they vanishes completely, then current will stop flowing due to vanishing of electric field, and hence potential difference becomes 0. Okay, so current will stop flowing. So we'll come to that diagram in our upcoming slides. So electric charges experience force under electric fields, leading to movement and current flow. So electric charges experience force under electric field. This is also we have discussed in our previous chapter. Okay, leading to movement and current flow. Leading to these electric fields and electric charges force experience force and start movement, then current start flowing. While free charges exist naturally in the ionosphere. Okay, so we know that a layer of Earth's atmosphere is ionosphere. Okay, so this ionosphere, as suggested by its name, free charges or ions are present naturally in this layer of atmosphere. Okay, in the ionosphere, free ions, free charges are present, exist naturally in this ionosphere. But atoms and molecules have bound electrons and nuclei. Okay, atoms and molecules have bound electrons. Okay, nuclei is bound and electrons are also bound with this nuclei. In the case of metal, outermost electron are only free, but innermost electron are bound. Okay, in case of other materials like insulators, all the electrons are bound. Okay, they are not free to move. So again, this figure. In bulk matter, like water with 10 to the power 22 molecules, electrons are not attached to individual nuclei due to close molecular packing. Okay, so in bulk matter like water, there are in 1 gram of water there are 10 to the power 22 molecules around. Okay, so like water with 10 to the power 22 molecules, electrons are not attached to individual nuclei. Okay, electrons are not influenced or under influence of one nuclei. They are under influence of attraction of other nuclei also due to close molecular packing, because molecules are packed very closely. So nuclei of different atoms are very close. So electrons are not attached to individual nuclei, but they are under influence of nuclei of other atoms also. Some materials keep electrons bound despite electric fields. Okay, some materials keep electron bound, like we have discussed in dielectrics. In the external field, electrons remain bound. Only distribution of negative and positive charges in between the molecule, stretching of molecule, we have discussed. Okay, only dipole moment is created, but electrons are still bound to the molecule. Okay, some materials, like we have discussed dielectrics, insulators, keep electron bound despite of external fields, despite of external electric fields, while conductors, especially metals, allow electron movement under the electric fields. But metals and conductors allow the movement of free charges, say electron, under the electric fields. In solid conductors, current flow through negatively charged electrons among fixed positive ions, unlike electrolytic solution. Okay, in solid conductors, current flow through negatively charged electrons. Okay, only negative charge, only electron flows in solid conductors. Okay, among fixed positive ions, or positive ions are not free, they are stationary or bound to each other. Unlike electrolytic solution, in electrolytic solution there are positive and negative ions both. Okay, so in electrolytic solution, current is due to both positive and negative ions. Unlike electrolytic solution where both positive and negative ions move, both negative and positive charges move. Without an electric field, electrons move thermally. Okay, when there is no electric field across the conductor, if across any conductor there is no electric field, then electrons move thermally, and this motion is random in any direction. So in absence of electric field, electrons move thermally, colliding with fixed ions and with each other. Okay, in the absence of electric field in conductor, electrons move thermally due to the temperature of the conductor. Okay, if we increase the temperature, the randomness of electrons also increases. Okay, so electron move thermally, colliding with fixed ions and with each other. These collisions maintain electron speed but randomized direction. So these collision maintain the electron speed, but the direction of their movement is random, but randomized direction. They will move in any direction. With no preferential direction, equal number of electrons travel in opposite direction, resulting in zero net current. Okay, when there is no electric field present, external electric field present, we can say that equal number of electrons travel in the opposite direction. If any n number of electrons are moving in forward direction, then same n number of electrons are moving in backward direction, because their movement is random. We cannot determine a fixed direction in which they are moving. They are completely random. So we can say equal number of electrons travel in opposite direction also. If n number of electrons are moving in forward direction, n number of electrons are moving in opposite direction. Okay, which results in zero net charge, zero net current. The current due to forward movement of electrons is equal and opposite to the current produced due to the backward movement of electrons. So net current in the conductor will be zero in the absence of external electric field. So in the absence of external electric field or external potential that we use to give with the help of wires, with the help of batteries, when we connect this end of conductor with the battery terminals, then potential difference is created, due to which electric field is created, and electrons start moving in the specific directions. But in the absence of electric fields, electron travel in random direction, results in zero current. When applying an electric field to a cylindrical conductor of radius r, now we are coming to that diagram. Okay, when applying an electric field to a cylindrical conductor of radius r, consider placing two thin circular dielectric discs. So why we are placing this dielectric disc? Because if we put any charge on the conductor, charge will flow, because this is conductor na, so it will allow the movement of charges. So we want to fix the charges to maintain the potential difference. So we are applying the potential difference with the help of dielectric disc. Okay, so we are charging this dielectric disc. This dielectric disc is charged with positive charge, and this is given negative charge, plus q and minus q. When applying an electric field to a cylindrical conductor of radius r, consider placing two thin circular dielectric discs with plus q charge on one end and minus q charge on the other end. So what will happen, as we have already discussed in brief, this creates an electric field directed from positive to negative charge. So these positive and negative charge will set up electric field from positive to negative charge. Electron accelerate towards the positive charge. So electrons present in this conductor will accelerate towards the positive charge in the direction opposite to this electric field to neutralize it. So they will move towards positive charge to neutralize this charge, creating a temporary current that stops after neutralization. So it will create a movement of these electrons towards this positive charge, will create a current due to movement of electrons, but this current is temporary. Okay, it will stop when these charges are neutralized. So these electrons will neutralize this positive charge, and the positive charges produced due to movement of electrons in this section will neutralize this negative charge, due to which electric field vanishes and potential difference also becomes zero. So then flow of electrons stop and current also stops after a while. Electrons accelerate towards the positive charge to neutralize it, creating a temporary current that stops after neutralization of the charge. To maintain a continuous current, the cylinder ends must receive fresh charges to replace neutralized one. Okay, if we want to maintain the current, if we want to maintain the flow of electrons or any charges, then we have to put fresh charges on these terminals continuously. Okay, So to maintain continuous current, these cylinder ends must receive fresh charges to replace the neutralized ones. Okay, the same mechanism is happening in the cell. What is the mechanism of cell? Chemical reactions are going on, and there is continuous accumulation of charges across the terminals. Okay, positive charges accumulate on one terminal, negative charges accumulate on another terminal. Okay, due to this chemical reaction, there is continuous accumulation of charges. Okay, so both the ends of the cell will receive fresh charges after neutralization of previous one. Okay, so this potential difference is maintained for a cell, and this is constant. After some time, when we use the cell, that chemical reaction begins to stop. Okay, so that chemical reaction, when this chemical reaction stop, the accumulation of charges also stop. Means there is a cut from the receiving fresh charges from the chemical reaction. We know that chemical reaction has stopped, then the accumulation of fresh charges on the terminals also stop, due to which potential difference that is being created by these charges on the terminals of the cell vanishes, becomes zero, due to which cell stop working. Okay, so this is the mechanism of the cell. We have to give the fresh charges to these ends continuously to maintain a steady current. To maintain continuous steady current, the cylinder end must receive fresh charges to replace the neutralized one, establishing a steady electric field within the conductor. Devices like cells or batteries provide this mechanism. Okay, so devices like cells or batteries, as I have already mentioned, that cells or battery provide this mechanism. The chemical reaction that is going within the batteries or cells provide fresh charges and maintain the continuous current, which we will study later in this chapter. So thank you. I hope you enjoyed and understood well the session.